What is blockchain? Understanding blockchain is fundamental to grasping how Web3 applications function. At its core, a blockchain is a distributed database that maintains a continuously growing list of records called blocks, which are linked and secured using cryptography. Each block typically contains a cryptographic hash of the previous block, a timestamp, and transaction data. Blockchains are inherently resistant to modification of the data and are an example of a distributed computing system with high Byzantine fault tolerance. Decentralized consensus can thus be achieved with a blockchain. This makes blockchains suitable for the recording of events, medical records, and other records management activities such as identity management, transaction processing, and proving provenance. The provided pseudocode captures the concept of a blockchain using simple JavaScript syntactic elements. It starts by defining a function createNewBlock, which simulates the creation of a new block in the chain with a hash, data, and the previous block's hash. Then, it initiates a blockchain with a single genesis block, the first block in the chain with a hard-coded previous hash of 0 and an arbitrary genesis block data string. Lastly, the addBlock function illustrates how new blocks, containing new sets of transactions or data, are appended to the chain. This simplified representation mirrors the principles of immutability and chain continuity in actual blockchain implementations. The encrypt function, which would typically involve a cryptographic hash function, is oversimplified for the purpose of this explanation. Decentralization versus centralization. Decentralization and centralization are foundational concepts in the discussion of blockchain technology and Web3. Centralization refers to the concentration of control and decision-making authority in a single entity or group, while decentralization distributes this across multiple nodes or participants, often with the goal of reducing single points of failure and increasing transparency and security. In the code above, we are using the Web3.js library to connect to a decentralized Ethereum node. This encapsulates the essence of decentralization in Web3. Instead of connecting to a central server, Web3 applications interact with a network of nodes distributed around the world, which ensures no single entity has control over the entire network, enhancing the principles of decentralization. Introduction to Ethereum. Ethereum is a decentralized platform that allows for the creation and execution of smart contracts and decentralized applications, DApps, without any downtime, fraud, control, or interference from a third party. The native cryptocurrency of the Ethereum network is called Ether, ETH. Ethereum operates on a blockchain, which is a distributed ledger technology that maintains a continuously growing list of records, called blocks, which are linked and secured using cryptography. While there is no direct code associated with the concept of Ethereum, as it is a platform, understanding Ethereum is essential before diving into coding with Web3.js, a collection of libraries which allow you to interact with a local or remote Ethereum node using HTTP, IPC, or WebSocket. The key takeaway is that Ethereum extends the blockchain concepts initially introduced by Bitcoin to support more complex financial interactions and decentralized applications through its programmable smart contracts. Smart contracts and their purposes. Smart contracts are self-executing contracts with the terms of the agreement directly written into lines of code. They run on a blockchain network, which means they are stored on a public database and cannot be changed. These contracts are executed automatically when predetermined conditions are met, without the need for intermediaries. Smart contracts form the backbone of decentralized applications, DApps, on blockchain networks. Unlike traditional contracts, they are transparent, irreversible, and tamper-proof. They facilitate, verify, or enforce the negotiation or performance of a contract digitally and provide a high level of security while saving time and reducing transaction costs. Consensus mechanisms, proof of work, proof of stake. Consensus mechanisms are fundamental protocols that underpin blockchain technology, enabling distributed systems to agree on a single version of the truth, even in the presence of dishonest participants. Two prominent consensus mechanisms in blockchain are proof of work, POW, and proof of stake, POS. POW requires participants to solve complex cryptographic puzzles, which consumes computational resources. POS, on the other hand, allows validators to participate in the consensus process by staking their coins as a form of financial commitment. Proof of work, POW, is used in blockchains like Bitcoin, where miners compete to solve a cryptographic puzzle, and the first one to solve it gets to add a new block to the blockchain. This process secures the network but is energy intensive. Proof of stake, POS, is a newer consensus mechanism used in blockchains like Ethereum 2.0, where validators are chosen to create new blocks based on the amount of cryptocurrency they hold and are willing to stake or lock up as security. POS is considered more energy efficient than POW. Public and private keys. In the world of blockchain and cryptocurrencies, security is of utmost importance. Public and private keys are the cornerstone of blockchain security. A public key is like your home address, which you can share with others to receive messages. A private key is like the key to your home, which you keep secret to decrypt messages intended for you. This code uses the Node.js crypto module to generate a pair of RSA keys, which can be used as public and private keys. The generate key pair sync function creates the keys with a specified modulus length of 2048 bits for security. It then exports the keys to a printable format, PEM, and logs the public and private keys to the console. It's important to keep the private key secure, as it is used to decrypt data encrypted with the public key. Wallets and their function. In the context of blockchain and cryptocurrencies, a wallet is a digital tool that allows users to store, send, and receive digital assets like cryptocurrencies. Wallets can be software-based, such as mobile apps or web applications, or hardware-based, like USB devices designed specifically for cryptocurrency storage. They manage private keys, which are essential for accessing cryptocurrency funds securely. Wallets don't actually store cryptocurrencies, but manage the cryptographic keys that are needed to access and transfer the digital assets recorded on the blockchain. A typical wallet interacts with the blockchain to update balances after transactions and provides an interface for the user to initiate new transactions. Wallets safeguard private keys using encryption and often provide backup mechanisms to prevent loss of access. Introduction to Web3.js and Ether.js libraries. Web3.js and Ether.js are JavaScript libraries that allow interaction with a local or remote Ethereum node via HTTP, IPC, or WebSocket. Web3.js was one of the first JS libraries to connect websites to the Ethereum blockchain. Ethers.js is a newer, more modular library. Both offer similar functionalities like creating wallets, sending transactions, and interacting with smart contracts, but they have different designs and syntaxes. The code shows how to initialize Web3.js and Ethers.js with a provider. Providers are a gateway to the Ethereum network, allowing you to query and interact with the blockchain. In the Web3.js example, we require Web3, create an instance of Web3, and connect to the mainnet via an Infura endpoint. In the Ethers.js example, we require Ethers, and specifically extract the JSON RPC provider to connect to the network. Both examples use Infura, a service providing Ethereum nodes without needing to run one locally. Replace your Infura API key with your actual Infura API key to connect. Node.js and NPM installation. Before diving into Web3 development, you need to set up your environment, which includes installing Node.js and NPM, Node Package Manager. Node.js is a JavaScript runtime that allows you to run JavaScript on the server side, and NPM is a package manager that enables you to install, share, and manage dependencies in your projects. While there isn't a code snippet required for installing Node.js and NPM, it typically involves downloading the installer from the official Node.js website and running it on your machine. During the installation process, NPM is also installed as it comes bundled with Node.js. After installation, you can verify the installation by opening a terminal and running node-v and npm-v to check the installed versions of Node.js and NPM, respectively. IDE setup, e.g., Visual Studio Code. Integrated development environments, IDEs, like Visual Studio Code, VS Code, are essential for efficient coding, debugging, and managing projects. VS Code, a popular choice for JavaScript and Web3 development, offers extensive support for these technologies through its built-in features and extensions. This code snippet demonstrates how to install an extension in VS Code via the command line. The specific extension ms-vscode.node debug2 adds enhanced debugging capabilities for Node.js applications. Similarly, developers can install other necessary extensions such as Solidity support for smart contract development or linters for code quality. Installation and configuration of Web3.js. Web3.js is a JavaScript library that allows you to interact with a local or remote Ethereum node using HTTP, IPC, or WebSocket. It provides an API to interact with the Ethereum blockchain and its ecosystem. To begin using Web3.js, you first need to install it using Node.js and npm. The code snippet is a command run in the terminal. It uses npm, Node Package Manager, to install the Web3.js library. Once executed, npm fetches the Web3.js package from the npm registry and installs it in your project's Node modules directory, allowing you to require or import it in your JavaScript files. Using test networks, e.g. Ropsten, Rinkeby. Test networks are versions of the Ethereum blockchain that are used for testing purposes. They are free to use and simulate the main Ethereum network, mainnet, without the risk of losing real money. Common test networks include Ropsten, Rinkeby, Kovan, and Goerli. They allow developers to deploy and test their smart contracts and DApps before going live on the mainnet. To interact with these test networks, developers use faucets to get free test ether. In the code provided, we start by requiring the Web3 library, which is essential for interacting with the Ethereum blockchain. We then create an instance of Web3, initializing it with Ropsten's network address provided by Infura. The getBalance function is an asynchronous function that fetches the balance of a given Ethereum address using the web3.eth.getBalance method. This balance is then converted from WEI to Ether for readability. Finally, we call getBalance on a test address to demonstrate how to retrieve an account's balance on the Ropsten network. MetaMask setup and usage. MetaMask is a popular browser extension that serves as a cryptocurrency wallet connected to the Ethereum blockchain. It allows users to interact with Ethereum and Ethereum-compatible blockchains through web applications, DApps. For Web3 development, MetaMask is used to authorize transactions and sign messages. Setting up MetaMask involves installing the extension, creating a wallet, and connecting it to a web application. The provided code snippet demonstrates how to connect to MetaMask using JavaScript. The Ethereum object is provided by the MetaMask extension to interact with the user's wallet. The connect MetaMask function uses Ethereum.request with the method eth_request_accounts to ask the user's permission to access their MetaMask accounts. If the user approves, it logs the first account address. If an error occurs, e.g., user denies access, it logs the error. If MetaMask is not installed, it prompts the user to install it. Using faucets to get test ether. During Ethereum application development, you'll often need to test transactions without using real ether. That's where testnets and faucets come in. Testnets simulate the Ethereum blockchain, and faucets provide you with test ether for free. Here, we'll walk through getting test ether from a faucet. Using a faucet to obtain test ether typically involves visiting a website specific to the testnet you are using, e.g., Rinkeby, Ropsten, Kovan, etc., entering your wallet address and requesting ether. Some faucets may have additional steps like social media verifications or rate limits to prevent abuse. After the request has been made, the faucet will send a small amount of test ether to your wallet, which you can use to deploy smart contracts or test transactions on the testnet. Web3.js Library Overview. Web3.js is a collection of libraries that allow you to interact with a local or remote Ethereum node using an HTTP or IPC connection. It's the bridge between the Ethereum blockchain and a JavaScript front-end application. This topic does not require code, as it's a conceptual overview. Understanding Web3.js involves grasping how it connects your web application to the Ethereum blockchain, enabling functionalities such as sending ETH, interacting with smart contracts, and managing Ethereum accounts. Connecting to an Ethereum node with Web3.js. To interact with the Ethereum blockchain, applications use an instance of the Web3.js library to connect to an Ethereum node. This node can be a local node or a remote service like Infura. Below is the basic usage example that demonstrates how to establish a connection using Web3.js. In the code, we first import the Web3.js library. We specify the Ethereum node's URL and create a new Web3 instance by passing in an HTTP provider with our node URL. This provider facilitates communication with the Ethereum node through HTTP. Then, we test the connection to the Ethereum node by using web3 eth.net.is listening. If the promise resolves, it prints a success message to the console. If there's an error, the promise is rejected, it catches the error and prints an error message. Interacting with Ethereum networks. Web3.js is a JavaScript library that allows you to interact with a local or remote Ethereum node using HTTP, IPC, or WebSocket. It can be used to send Ether, interact with smart contracts, and access blockchain data. To start, you need to set up a connection to an Ethereum network. This code initializes Web3.js and connects to the Ethereum main network using Infura as a provider. Your Infura API key should be replaced with your actual Infura project API key. Infura provides an easy way to connect without running your own Ethereum node. Once initialized, you can use Web3 to interact with the Ethereum blockchain. Balance and transaction queries. In this section, we will learn how to use Web3.js to query the balance of an Ethereum account. We will use the getBalance method provided by the web3.eth object, which requires the account address and an optional argument to specify the block number. In the provided code, we first call the getBalance function, passing it the address of the Ethereum account for which we want to get the balance. The getBalance function returns a promise which resolves to the balance in Y. We use .then to handle the resolved promise, and inside the callback, we use web3.utils.fromY to convert the balance from Y to Ether. Finally, we log the balance to the console in units of ETH. Subscriptions and filters. In Web3.js, subscriptions and filters are used to react to changes in the state of the Ethereum blockchain. For example, they allow you to listen to new blocks or events. When utilizing subscriptions, you need a connection to a WebSocket-enabled Ethereum node. The code demonstrates how to subscribe to logs from a specific smart contract address. The subscribe method is called on the web3.eth object, specifying the type of data to listen to, logs, and a filter object defining the contract address and topics, event signatures. The callback function is triggered whenever a matching log is detected on the blockchain, printing the result to the console. If a WebSocket connection is unavailable, filters can accomplish a similar, but more limited functionality by polling for events. Event listening with Web3.js. In the context of Ethereum and Web3.js, events are logs, which are emitted by smart contracts when certain actions occur. These logs are part of the Ethereum blockchain. Event listening in Web3.js is a feature that allows your application to react to specific contract events in real time. In this code snippet, myContract is a reference to a smart contract instance. myEvent is an event defined in that smart contract. The events.myEvent function is used to subscribe to myEvent. The filter object can be used to only listen for events with specific indexed parameters. The from block specifies the starting block number from which to listen to events. The callback function is called each time myEvent occurs, logging the event to the console. The data and changed events are different triggers that the event listener can respond to. Data for a log being added, changed for a log being removed, e.g., due to a blockchain reorganization. The error event handles any errors that occur during event listening. Using Web3.js utilities. Web3.js provides utility functions to convert between different units of Ether. One of the most commonly used conversions is from WAY, which is the smallest denomination of Ether, to Ether itself. The code uses the fromY function from the web3.utils module to convert a value denominated in WAY to Ether. Here, 210,000Y is being converted to Ether. The function returns a string representing the value in Ether. Solidity language basics. Solidity is a contract-oriented, high-level language for implementing smart contracts. It is designed to target the Ethereum virtual machine, EVM. Let's look at a basic example of a Solidity contract, which illustrates the structure and syntax of defining a contract. The code starts with a pragma directive, which indicates the compiler version to use. The contract keyword initializes a new contract definition named simple storage. Inside the contract, uint stored data declares a state variable. The set function allows users to store a value, and the get function returns the stored value. The public keyword makes functions callable from outside the contract, and view signifies that get does not alter the blockchain state. Smart contract structure and syntax. In Ethereum, smart contracts are written in a high-level language called Solidity. The structure of a Solidity smart contract is somewhat similar to a class in object-oriented programming. It contains state variables, functions, function modifiers, events, and a constructor. This code defines a simple Solidity smart contract named simple storage. The contract includes a state variable stored data, a constructor to initialize the state, and two functions: set for updating stored data, and get for retrieving its value. The pragma keyword specifies the compatible Solidity compiler versions. The public keyword makes functions accessible outside the contract, and the view keyword indicates that get does not modify the contract state, enabling read-only access. The structure shows typical use cases of state management in smart contracts. Creating a basic smart contract. A smart contract is a self-executing contract with the terms of the agreement directly written into code. To create a basic smart contract, we will use Solidity, the most popular programming language for Ethereum smart contract development. In this example, we'll create a contract that stores and retrieves a value. The Solidity version pragma specifies the compiler version to prevent compatibility issues. Simple storage is the smart contract we're defining. It has a state variable stored data to store a number. Set is a function allowing anyone to update stored data with a new value. Get is a function that enables others to retrieve the stored value. Public means these functions can be called from inside and outside the contract, and view indicates that get does not modify any state variables. Compiling and deploying with Truffle. Truffle is a development environment, testing framework, and asset pipeline for Ethereum, aiming to make life as a developer easier. Compiling and deploying with Truffle simplifies the smart contract development process. Below, you'll find an example of how to use Truffle to compile and deploy a smart contract written in Solidity. This example shows a typical Truffle migration script for deploying contracts. The artifacts.require function is similar to Node's require, but instead, it's specific to Truffle and returns a contract abstraction that Truffle can deploy. The module.exports is a JavaScript pattern where the exported function gets a deployer object as an arg, which is provided by Truffle. The deployer.deploy function is then called with the contract abstraction, indicating that the migrations contract should be deployed when this migration runs. Using Remix IDE for quick prototyping. Remix IDE is an open-source web application that makes it easy to write Solidity smart contracts. It's convenient for quick development cycles and can interact with smart contracts directly from the browser. The given code is a Solidity smart contract for a simple storage system written in Remix IDE. The pragma directive specifies the compiler version to avoid any issues with future compiler updates. The simple storage contract has a single state variable, stored data, which holds a uint, unsigned integer. Two functions, set and get, allow users to store and retrieve the value of stored data. The set function updates the value, while the get function is marked as view because it doesn't alter the state, making it cost-free when called externally. Understanding gas and transaction fees. In Ethereum and other similar blockchains, gas refers to the unit that measures the amount of computational effort required to execute operations like transactions and smart contracts. Users must pay transaction fees to compensate for the computing energy required to process and validate transactions on the blockchain. These fees are calculated in gas and paid in the blockchain's native cryptocurrency, e.g. Ether for Ethereum. The code represents a JavaScript object that could be used to define a transaction in Ethereum. The to field specifies the recipient address. The value field is the amount of Ether to send, denoted in Y, where 1 Ether equals 10 to 18 Y. Gas is the limit of gas units that the transaction can consume, and gas price is the amount of Ether the sender is willing to pay per unit of gas, measured in Y. The total transaction fee will be the product of gas and gas price. ABI, Application Binary Interface, explained. In Ethereum, the Application Binary Interface, ABI, is essentially a blueprint for smart contracts and defines how to interact with them. It enables the conversion of human-readable function signatures into the encoding expected by the Ethereum network, and vice versa. Without an ABI, the JavaScript code wouldn't know how to format calls to a smart contract. The code snippet shows how to create a contract instance in Web3.js using the ABI and the contract's address. The ABI is passed as an array of objects, each representing a function, event, or constructor of the contract. The web3.eth.contract class is then used to instantiate the contract, allowing us to call its methods and listen to its events. Interacting with a smart contract using Web3.js. Interacting with smart contracts in Ethereum using Web3.js involves connecting to the Ethereum network and then reading data from or writing transactions to the smart contracts deployed on the network. The following snippet demonstrates how to set up Web3.js, connect to an Ethereum node, and interact with a smart contract. This code initializes a Web3 instance connected to the main Ethereum network via Infura. It requires your Infura project ID to connect successfully. The snippet declares a contract ABI, which is an array that defines the smart contract's methods and structures. Additionally, the contract address points to the deployed contract. After setting up the contract instance with ABI and address, an asynchronous function called contract function is declared to call a method named yourMethod on the contract. This is a read operation that does not make any state changes on the blockchain. Reading data from a smart contract. To read data from a smart contract in Ethereum, you can use the Web3.js library, which provides an easy-to-use API to interact with the Ethereum blockchain. When reading data, you're calling functions of the smart contract that don't make any state changes, don't alter the blockchain, meaning they're free and don't require a gas fee. This code snippet creates an instance of a smart contract using its ABI and address, allowing us to interact with it. The contract.methods.sum function call is a function call to a view or pure function of the smart contract, which reads data. The await keyword is used because the call returns a promise. The returned data is logged to the console. This is done inside an asynchronous function getContractData that can be invoked to retrieve the data. Executing transactions and function calls. To interact with a smart contract in Ethereum, you can send transactions to it. Transactions can change the state of the contract, typically by calling one of its functions. To send a transaction, you first need to set up a Web3 instance connected to an Ethereum node, and the smart contract ABI and address need to be known. Here's an example of how to execute a transaction that calls a smart contract function using Web3.js. The code first loads the Web3 module and sets up a connection to an Ethereum node. Next, it defines the ABI and address for the smart contract you want to interact with. Using the web3.eth.contract object, we initialize our contract instance. We specify the sender's address from address. We use the method's property of the contract to get a method object for my function with the necessary arguments, and then we call encode ABI to serialize the transaction data. Finally, we use web3.eth.sendTransaction to send the transaction, including the serialized data in the data field, and then we chain a then with a console.log to handle the promise. Handling transaction confirmations and receipts. When you interact with a smart contract on the blockchain by sending a transaction, it is crucial to handle the confirmation and receipt of the transaction. It helps you to ensure that the transaction was processed and to understand the result of the operation. This handling is done through JavaScript promises and event listeners using the Web3.js library. In the code snippet, we first call a method, myMethod, of our smart contract. We use the send function to initiate the transaction and provide the sender's address. The .on functions are event listeners for different stages of the transaction lifecycle. The transaction hash event provides the hash of the transaction as soon as it's available. The receipt event gets triggered when the transaction is mined, giving us the transaction receipt. The confirmation event fires for each subsequent block that is mined, up to 24 confirmations by default, but can be set otherwise. Lastly, the error event catches any errors that occur during execution. Creating tokens, ERC20, ERC721. The ERC20 token standard allows for the creation of fungible tokens on the Ethereum blockchain, which can be used in a variety of applications such as currencies, rewards, and voting rights. The following Solidity code demonstrates the creation of a basic ERC20 token. This code snippet shows a simple ERC20 token contract using the Open Zeppelin contracts library. It imports the ERC20.sol file, which contains the standard logic for ERC20 tokens. The MyToken contract inherits from ERC20 and calls its constructor with the name and symbol of the token. The mint function is used to create the initial supply of tokens and assign it to the wallet deploying the contract. Advanced Solidity topics, modifiers, error handling, events. Modifiers in Solidity are code fragments used to change the behavior of functions. They can be used to add preconditions, postconditions, or to ensure certain conditions are met before executing function logic. They're particularly useful to avoid repetitive code and to enhance readability and maintainability. The code defines a modifier-only owner that requires the msg.sender to be equal to an owner state variable. The SOR is where the modified function's code is executed. The change ownership function uses this modifier, meaning that only the current owner can successfully call change ownership. Developing decentralized applications, DApps. A decentralized application, DApp, is an application that operates autonomously on a blockchain network, typically with a combination of smart contracts and a user interface. In Ethereum, smart contracts are written in Solidity or Viper and are deployed on the blockchain, where they run exactly as programmed without censorship or third-party interference. DApps interact with these smart contracts via a Web3 client using libraries such as Web3.js or Ethers.js in JavaScript. The code snippet illustrates how to initiate a connection to an Ethereum node using the Web3.js library, which allows the DApp to interact with a smart contract. Web3 is instantiated with an HTTP provider pointing to the node. The contract ABI and contract address are used to create an instance of the contract object. The init async function demonstrates making a call to a smart contract's read-only method, myMethod. The returned data is logged to the console. Error handling is provided with catch to log any exceptions that occur during initialization. Managing user accounts and private keys. In the context of Ethereum and other blockchain platforms, managing user accounts and private keys is crucial for ensuring security and access control. A user account is represented by an address, and the corresponding private key is used to sign transactions to prove ownership. It's imperative that private keys are managed securely to prevent unauthorized access and potential loss of funds. The provided code snippet demonstrates how to create a new Ethereum account and private key using the Web3.js library, which is a popular JavaScript library for interacting with the Ethereum blockchain. The web3.eth.accounts.create function generates a new account and private key. The created account object includes the address and private key, which are logged to the console. In practice, private keys should never be exposed like this and should be stored securely using appropriate secret management solutions. Integrating with front-end frameworks, React, Angular, etc. To create a DApp, one needs to integrate smart contracts with a front-end application. React is a popular choice for this purpose due to its component-based architecture and vast ecosystem. The integration process involves setting up a Web3 provider, connecting to Ethereum networks, and then interacting with smart contracts, using contract ABIs and addresses. This React component initializes Web3, the accounts, and the contract. It imports the Web3 library to interact with the Ethereum network and the compiled contract JSON. Upon mounting with useEffect, it sets up the Web3 instance, fetches and sets the user's accounts, identifies the network, and creates a contract instance using the ABI and the deployed network address. This contract instance can now be used to interact with the smart contract. Contract testing with Mocha and Chai. Testing is a critical phase in smart contract development, ensuring that the contract will perform as intended when deployed on the blockchain. For Ethereum smart contract testing, developers commonly use the Mocha testing framework along with the Chai assertion library. Mocha provides the environment to run tests, while Chai offers a rich set of assertions to validate the results of smart contract function calls. In the provided code, we begin by acquiring the contract abstraction for myContract. The contract function is used to define a suite of tests. For each test, a new instance of the contract is obtained using before each to ensure isolation between tests. It defines an actual test, which in this case checks the initial value is set to 0. The assert.equal method from Chai asserts that the expected value matches the actual value. If it doesn't, the provided error message is returned. This establishes a basic testing pattern for a smart contract function using Mocha and Chai. Security considerations and best practices. A reentrancy attack allows an attacker to repeatedly call the withdrawal function to drain a contract's funds. The attack can occur when a contract sends ETH and then allows the control to be transferred to an external contract before updating its state. To prevent this, the state should be changed before calling an external contract. This example showcases a vulnerability rather than a best practice. The withdraw function is susceptible to reentrancy because it interacts with an external address via msg.sender.call before deducting the amount from the user's balance. A secure practice would be to update balances mssender -- amount before sending ETH. This is known as the checks effects interactions pattern. Setting up a Web3 front-end project. The first step in setting up a Web3 front-end project is initializing the project directory with a package manager like npm or yarn. This will create a package.json file, which will manage all of your project's dependencies. The mkr command creates a new directory for your project. cd changes the current directory to your newly created project. npm init initializes a new npm project and creates a package.json file with default settings. Interacting with contracts using ethers.js. Ethers.js is a lightweight JavaScript library that allows you to interact with the Ethereum blockchain. It can be used to connect to Ethereum nodes via JSON RPC, send transactions, interact with smart contracts, and more. Below, we show how to use Ethers.js to create an instance of a smart contract and call one of its functions. First, we import the Ethers library. We create an async function called interactWithContract. Inside, we instantiate a provider to connect to the Ethereum network. We then get a signer from the provider, which is needed to send transactions. Next, we define the contract's address and its ABI, Application Binary Interface, which is an array that describes how to interact with the contract. We create a new contract object, passing it the address, ABI, and signer. Finally, we call some function on the contract, which returns a transaction response that we log to the console. Using Web3 providers, e.g. Infura, Alchemy. In Web3 development, providers act as a bridge between a blockchain network and a web application, allowing the app to communicate with the network. Infura and Alchemy are popular providers that offer APIs to interact with Ethereum and other blockchains without running a full node. To get started, you will need to sign up for Infura or Alchemy, create a project, and obtain an API key or URL. This code snippet demonstrates how to set up a Web3 provider using Infura. It begins by importing the Web3 library and defining the project URL from Infura, which includes the project ID. The Web3 instance is created with an HTTP provider using the Infura URL endpoint. Finally, we use the created Web3 instance to interact with the blockchain, as shown with web3.eth.getBlockNumber, which returns the latest block number when called. Integrating MetaMask for user transactions. Integrating MetaMask for user transactions involves connecting the MetaMask wallet to your web application so users can interact with blockchain. First, you ensure that the user has MetaMask installed, then request access to their account. After successfully connecting, you can initiate transactions which the user can confirm through MetaMask. In this code snippet, a function, connectMetaMask, is defined to handle the connection process. It checks if the MetaMask extension is present. If not, it alerts the user to install MetaMask. Upon finding MetaMask, window.ethereum, it uses ethereum.request with the method ethRequestAccounts to prompt the user to connect their wallet. If the user grants access, their account address will be logged to the console. Otherwise, an error is logged indicating the user denied the connection. Building user interfaces for DApp interaction. To interact with a smart contract through a user interface, we need to connect our UI elements with blockchain functions. In this example, we'll create a simple button in our HTML that triggers a function of a smart contract using Web3.js. We'll assume we have a smart contract deployed with a function named myFunction that we want to call. This snippet shows a button in HTML with an ID of myButton, and JavaScript that uses Web3.js to connect to a smart contract. The Web3.eth.contract object is initialized with the contract's ABI and address. An event listener is added to the button to call myFunction of the smart contract when clicked. The transaction is initiated with the send method, specifying the user's address as the sender. If the transaction is successful, the result is logged to the console. Otherwise, errors are caught and logged. Handling multiple network and account changes. In decentralized applications, handling changes in users' accounts and the blockchain network they are connected to is crucial. These changes can occur when a user switches their active account in a wallet like MetaMask, or when they switch between networks, e.g., from Ethereum mainnet to Rinkeby testnet. Properly managing these events ensures the DApp stays responsive and up to date with the correct network and account data. The provided code snippet listens for two events emitted by the Ethereum provider object, usually injected by wallets like MetaMask. The accounts changed event is triggered whenever the user switches accounts in their wallet. It passes an array of accounts where you can check if the first, primary, account has changed from the previously known user account and update the application state accordingly. The chain changed event fires when the user switches the network they are connected to. A full page reload is often a simple way to reset the DApp state to align with the new network, though more sophisticated strategies may avoid reloading. Implementing real-time updates in DApps. Real-time updates in decentralized applications, DApps, are critical for a responsive user experience. One method to implement real-time functionality is using Web3 subscriptions, which allow your app to listen for specific events on the blockchain. For instance, you can subscribe to new blocks being added, or to events emitted by smart contracts when a state change occurs. Below is a basic setup using Web3.js to subscribe to event logs from a smart contract. The given code snippet starts by requiring the Web3 package and creating a new Web3 instance, connecting to a WebSocket-enabled Ethereum node at WS localhost 846. It then instantiates a new contract instance by providing the ABI and address of the deployed smart contract. Using mycontract.events.myEvent, we subscribe to the myEvent occurring within the smart contract, providing a callback function for immediate processing, and chaining to-on methods for handling data, changed, and error events. The data listener logs each event for real-time processing, while changed handles reorganizations in the blockchain where events may be removed, and error captures any issues encountered during the subscription. Overview of Decentralized Finance, DeFi. Decentralized finance, or DeFi, is an emerging financial technology based on secure distributed ledgers similar to those used by cryptocurrencies. DeFi platforms aim to recreate and improve upon traditional financial systems, such as banks and exchanges, with cryptocurrency technology. DeFi leverages blockchain and smart contract technology to facilitate financial transactions outside of traditional banking systems. It encompasses a wide range of financial services, including lending, borrowing, exchanging, and asset management, executed in a peer-to-peer fashion without the need for intermediaries. Transactions in DeFi are transparent, accessible to anyone with an internet connection, and operate on a trustless basis, meaning users do not need to trust a central authority for the system to function securely. Understanding and interacting with DeFi protocols. To interact with DeFi protocols, you must first connect your Web3-enabled application to a smart contract. This process typically involves creating an instance of a Web3 provider, initializing a Web3 object, and then connecting to the smart contract using its ABI and address. This code snippet creates a Web3 instance using Infura as a provider to connect to the Ethereum mainnet. After creating the Web3 instance, a contract instance is created using the ABI and contract address, which allows you to interact with the DeFi protocol. Introduction to non-fungible tokens, NFTs. Non-fungible tokens, or NFTs, are a class of digital assets that represent ownership or proof of authenticity of a unique item or piece of content, typically using blockchain technology. Unlike cryptocurrencies such as Bitcoin or Ethereum, which are fungible and can be exchanged on a one-to-one basis, each NFT has a distinct value and is not directly interchangeable with another NFT. This is often because NFTs are linked to specific assets, which could range from digital art and collectibles to real estate and more. The provided code snippet initializes a connection to the Ethereum blockchain using Web3.js and sets up a truffle contract based on the ABI, application binary interface, of a specific NFT contract. After defining the smart contract's address, the code sets up a Web3 provider using Infura. Then, init defines an asynchronous function getNFT_metadata that takes a token ID as an argument. The function uses the NFT contract instance to retrieve the URI of a token's metadata. This URI usually points to a JSON file hosted off-chain that contains information about the NFT, such as its name, description, and image or media associated with it. The comment denotes where additional code would be needed to fetch the actual metadata using the URI. Creating and managing NFTs. Non-fungible tokens, NFTs, are unique digital assets that represent ownership or proof of authenticity of a specific item or piece of content, usually on a blockchain. They are indivisible and cannot be exchanged on a one-to-one basis like cryptocurrencies. NFTs are primarily used in applications like digital art, collectibles, and online gaming. NFTs differ from cryptocurrencies in that each token is unique and can hold additional information, enabling them to represent individual pieces of content with proof of ownership. Deploying and interacting with NFT marketplaces. An NFT marketplace is a platform where users can mint, buy, sell, or trade NFTs, non-fungible tokens. Deploying an NFT marketplace involves creating a smart contract that handles the logic for these operations. The following code sample demonstrates how to deploy a simple NFT marketplace smart contract using Solidity and Truffle, which is a development environment for Ethereum. The code defines a simple NFT marketplace contract that extends OpenZeppelin's ERC-721 implementation. It sets the contract's owner upon deployment and implements a basic mint NFT function, allowing the creation of new tokens. Additional marketplace functions, such as buying or bidding on NFTs, would need to be implemented for a complete marketplace. The construction requires setting up a development environment like Truffle, creating a smart contract file, compiling the contract, deploying it to an Ethereum network, and then interacting with it through Web3.js in a JavaScript application. Composing multiple DeFi protocols. In the context of DeFi, decentralized finance, composing multiple protocols involves creating complex financial operations by leveraging the functionalities of various DeFi projects. This is akin to money Legos, where each protocol offers a building block that can be combined to form more complex structures. An example could be borrowing assets from one platform, providing them as liquidity in another, and then staking the liquidity provider LP tokens to earn rewards. The illustrated code provides an abstract view of how one might compose multiple DeFi protocols using JavaScript and the Web3.js library. It begins by borrowing Ether from the Aave lending pool, which is a decentralized lending protocol. Next, it adds liquidity to a Uniswap exchange pool, a decentralized exchange, DEX, which allows users to swap various tokens and provides liquidity. Finally, it stakes the received liquidity provider, LP, tokens in a staking contract to earn rewards. The specific contract methods, parameters, and handling of transaction receipts and events are not shown, but would be necessary for a fully functional implementation. Writing tests for smart contracts and DApps. Before writing tests for smart contracts and DApps, you must set up a testing environment. A common setup for Ethereum smart contract testing is to use the Truffle framework, which integrates with Mocha and Chai for running tests. Make sure you have Node.js and Truffle installed. The code above installs Truffle globally using npm and initializes a new Truffle project in your current directory. This sets up a basic project structure with a test directory where you'll create and run your tests. Using test frameworks, e.g., Truffle, Hardhat. In the development of smart contracts, testing is crucial to ensure the code behaves as expected before deployment to the blockchain. Test frameworks like Truffle and Hardhat come equipped with tools to streamline the testing process. These frameworks allow you to write and run tests written in JavaScript, which interact with your smart contracts in a controlled environment. The code above is an example of a test script using Hardhat and the Chai assertion library. It describes a test suite for a token smart contract. This suite contains a single test that checks if, upon deployment of the contract, the total token supply is assigned to the owner's balance. The ethers library is used to get the list of signers and to create and deploy the token contract. Then it retrieves the owner's balance and compares it with the total supply using Chai's expect to assert equality, ensuring the contract initializes correctly. Debugging smart contracts and transactions. Debugging is a critical part of smart contract development. It involves identifying and fixing issues in your code to ensure that it behaves as expected. Smart contracts, once deployed, are immutable and cannot be altered, making it essential to catch errors beforehand. To debug transactions, developers often use tools like Truffle, Ganache, and Remix, or testnets to simulate the conditions of the Ethereum mainnet. Using Truffle, one of the most popular development frameworks for Ethereum, you can debug transactions by running the above command with the specific hash of the transaction you want to investigate. Truffle Debugger starts, allowing you to step through transaction execution, examine variables, and evaluate conditions at different stages of the transaction. This can reveal where things went wrong and what data was affected at each step. Deploying smart contracts to mainnet. Deploying a smart contract to the mainnet is the final step of making your contract live and interactable by anyone on the blockchain. The process involves using a framework like Truffle or Hardhat, compiling the contract, and sending a deployment transaction through a Web3 provider. An Ethereum wallet with enough Ether to pay for gas fees is necessary. Always ensure to test your contracts thoroughly on testnets before the mainnet deployment. This code snippet demonstrates how to deploy a smart contract using Hardhat, which is a development framework for Ethereum. First, it imports the ethers library from Hardhat. In the main async function, it gets the contract factory for your contract, which is a placeholder for your actual contract name. Then, it calls deploy on that factory, passing in any necessary constructor arguments, and waits for the deployment to finish. After deployment, it prints the contract address to the console. Lastly, the main function is invoked, and any thrown errors are caught and logged. Verifying smart contracts on Etherscan. Verifying a smart contract on Etherscan is an essential step that ensures users can read the contract's code and interact with it with confidence. It involves flattening the contract, if composed of multiple files, and matching its bytecode to the one deployed on the Ethereum blockchain. This process requires the source code, the compiler version, the optimization settings, and constructor arguments, if any. Since this is a non-coding conceptual explanation, no actual code is involved in the process of verification itself. Verification is completed through Etherscan's user interface. You provide the source code and other required information, and Etherscan processes this to verify that the bytecode produced by compilation matches the deployed contract. Once verified, the contract will show as verified, and its source code will be visible to the public on Etherscan's website, thus increasing transparency and trust. Using deployment tools and plugins. Truffle is a popular development framework for Ethereum that provides a suite of tools for writing, testing, and deploying smart contracts. It takes care of many tasks, such as compilation, migration, and network management. This sample migration script is written in JavaScript for use with Truffle. It imports the contract with artifacts.require, which is similar to Node's require. The module.exports function is the deployment script that Truffle will run. Inside it, deployer.deploy is invoked with the contract to deploy it to the blockchain. Scaling solutions and Layer 2 technologies. As the Ethereum blockchain grew in popularity, it encountered problems with scalability, leading to high gas fees and slower transaction times. To address these issues, various scaling solutions were developed, including Layer 2 technologies that operate atop the main Ethereum blockchain, Layer 1. Layer 2 solutions aim to reduce congestion and cost while increasing transaction throughput. Examples include state channels, plasma, rollups, and sidechains. The provided code initializes a provider specifically for the Optimism network, which is a Layer 2 scaling solution for Ethereum. It uses the Ethers library, a popular Ethereum JavaScript library, in conjunction with the Optimism/provider package to connect to the Optimism network. The code fetches the latest block number from the Optimism chain, demonstrating a simple interaction with a Layer 2 network. This operation is analogous to interacting with the main Ethereum network, but transactions are processed more efficiently and with lower fees. Cross-chain interoperability. Cross-chain interoperability refers to the ability of different blockchain networks to communicate and interact with one another, allowing for the exchange of assets and information. This is crucial in creating a more interconnected and functional blockchain ecosystem. There are several methods to achieve this, such as using cross-chain bridges, sidechains, and layered protocols. In the case of JavaScript and Web3, developers can utilize libraries or APIs that help facilitate cross-chain operations. The provided code sets up a JavaScript environment to interact with a cross-chain bridge using Web3.js. It first includes the Web3 library, defines the ABI and address for a cross-chain bridge contract, and then instantiates two Web3 instances, each connected to a different blockchain, source chain RPC URL and destination chain RPC URL. A bridge contract object is created on the source chain, and an async function, transfer assets to another chain, is defined to execute the asset transfer using the bridge. The function assumes availability of a transfer method in the bridge contract, which is to be called with toAddress and amount as arguments, along with the transaction initiator's address from address. Decentralized Autonomous Organizations, DAOs. Decentralized Autonomous Organizations, DAOs, are entities that operate without centralized control, governed by smart contracts and collective decision-making of its members. They facilitate collaboration and decision-making through blockchain technology, allowing for transparent and democratic management. While DAOs are not typically created or managed with simple scripts, they do rely heavily on code for their operation. They are often built on platforms like Ethereum, using smart contracts to encode the rules of the organization. The creation of a DAO involves writing and deploying these smart contracts, which govern the DAO's operations, including proposals, voting mechanisms, membership, and treasury management. However, for this overview, there is no specific code snippet involved. Oracles and real-world data. In the context of blockchains and smart contracts, an oracle is a bridge that connects on-chain smart contracts with off-chain real-world data. Smart contracts inherently cannot access data outside their network, which presents a limitation for developing real-world applications. Oracles serve as data feeds that provide external data, like temperature, pricing information, etc., to smart contracts, enabling them to execute based on real-world events and information. This topic does not require an actual code example, since it involves a conceptual understanding of how oracles integrate with smart contracts. Oracles can be software-based, fetching data from online sources, or hardware-based, sourcing information from the physical world. This data can then be used to trigger certain functions in a smart contract, such as adjusting the price on a decentralized exchange, settling a bet, or initiating an insurance payout after certain conditions are met. Advanced use cases, decentralized identity, supply chain, etc. Decentralized identity allows users to own and control their personal identity information without the need for central authorities. This can be achieved using blockchain technology and smart contracts. A common protocol for decentralized identity is the ERC-725 standard. The code initializes Web3 and sets a provider, typically where your Ethereum node is running. An instance of ERC-725-based smart contract is created using its ABI and address. The getIdentity function, asynchronously fetches identity data of a given address using the contract method identity, which would return associated identity data if implemented in the contract. Please note that actual implementation may vary based on the specific contract. This is only an illustrative example to demonstrate interaction with a decentralized identity smart contract. Blockchain analytics and monitoring. Blockchain analytics and monitoring involve tracking and analyzing transactions, smart contracts, and on-chain activities to gain insights or detect suspicious behaviors. Tools for analytics may include blockchain explorers, dedicated analytics platforms, or custom-built scripts. Monitoring can help in compliance, security, and understanding ecosystem trends. Since the focus of this topic is conceptual, there isn't a specific code snippet to provide. Blockchain analytics and monitoring don't necessarily involve writing code. Instead, they often require the use of tools and platforms designed for these purposes, such as Etherscan for Ethereum or BitQuery for multiple blockchains. Web3 security, audits, common attacks, and how to prevent them. In the Web3 space, security is a paramount concern due to the immutable and high-value transactions involved. To ensure the integrity of smart contracts and applications, various security practices, such as audits and awareness of common attacks, are crucial. Preventative measures are often employed to avoid security breaches. The provided code is an example of a testing script written in JavaScript for a smart contract. It uses a testing framework like Mocha or Truffle. It's important to write comprehensive tests for all smart contract functions to check for common vulnerabilities, such as those that only the owner can access certain functions and protections against reentrancy, overflow, underflow attacks. Regular testing and audits can help identify security flaws before deployment.